workshop on inconsistent science and scientific pluralism. Our speaker is Ótavio Bueno, and you know him. So he will be talking about scientific pluralism, consistency preservation, and inconsistency toleration.
All right.
50 minutes.
Well, first I'd like to thank both Luis and Maria for the lovely invitation to return to Mexico City. It's always a treat to be back here, especially in the presence of so many great people and on this great topic to talk about. So I'm going to try to address one of the questions that Luis and Maria raised about the connection between scientific pluralism and inconsistent scientific theories. The bulk of the paper will be a discussion of how to make sense of those inconsistencies, and then we're going to see what impact that has to debates on pluralism. So first, just to be absolutely clear, of course, there is, and Derek talked a little bit about that yesterday, there is a variety of different senses of pluralism in the literature. Of course, you can be a pluralist about different kinds of things, right? You might be an ontological pluralist. The world itself is sort of a plurality of things. You may be a methodological, there's a plurality of methods. A theoretical pluralist, different theories, right? An axiological pluralist, different names of scientific research. And so for the purpose of today's talk, I'm not going to bring in fine-grained distinctions about that. I'm going to just lump all of those kinds of pluralism together in this kind of what I'm calling scientific disunity pluralism, right? According to it, there is a variety of domains, scientific domains, and a variety of scientific theories to study those domains. And these theories are empirically adequate relative to their own domain. So there are various domains that can be studied differently, right? According to different scientific theories. Of course, the opposite view here is scientific monism, right? According to it, well, we only have a single domain, huge domain of investigation, and that's the domain that the scientific theories apply, right? So that's the rough and ready distinction that I'll be operating with for the purpose of this talk. Now, to put my cards on the table, I think that any monist view is wrong, right? And I cannot see how a monist picture can really make sense of contemporary science. And we can talk about that later on. But I'm almost inclined to say that any view that actually entails some form of monism of that kind is just wrong. Right, it's a wrong reduction of what it is. Of course, there is a long-standing tradition of attempting to create an image for science in which some form of monism is in place, but I think that kind of image is unsustainable, right, and indefensible. Just a quick and dirty argument here. Consider just a few scientific domains and try to piece them together, right? What is it that quantum field theory and pediatrics have in common? How about molecular biology and cultural anthropology? Think about biochemistry and sociology, right? I want to say, of course, that there's absolutely nothing in common with these fields. They don't share the same goals, methods, theories, approaches, right? And of course, they are all part of science. And I think as an attempt of making sense of science, you need to understand that plurality. Anyone that tries to say, no, there is something in common about all of that, right? You might be a Popperian, so they're all trying to use modus tollens and refute that theory. Well, if that's their best shot at being a monist, then I think you lost the content of the science you're trying to understand. You're operating at a level of idealization that's so high that has nothing to do with real science anymore, okay? So what I would like is that you go back as an attempt at making sense of science, you look at how science is done. Because I think that's one of the goals of philosophers of science. That is the way I understand it. And I find, honestly, monism a non-starter, right? I won't say the same thing about monism, about logic, but then we can talk about that on Friday, right? Okay, so the broader question of today's talk is then to consider how these views, pluralism and monism, right, are impacted by the presence of inconsistent scientific theories, right? And in particular, inconsistent theories that are inconsistent with one another.
Okay,
Yeah.
that's what I want to ask.
Yeah.
You mean internally inconsistent?
That's right. I'm going to clarify here. Again, to put my cards on the table, typically scientific theories are not self-contradictory, right? They're not meant to be that way. If that happens, it's a mistake.
But that depends how you individuate theory too.
It does. And I'm going to talk a little
If you
bit
say
about
chemistry, then it's going to be contradiction.
well, chemistry is not a scientific theory, right? It's a whole field, right? But you don't have theories that are, okay, yes, I have this great theory in chemistry that actually explains everything because it's contradictory, right? You don't find anything like that, right? And I think with good reason.
But it doesn't necessarily mean that it's not contradictory. It's that it's not trivial and maybe it was not explosive, it was contradictory.
That's right. So, and that's right. Part of the issue, and I'm going to spend quite some time trying to be clear about what is it that is at issue here, right, on that. So, in particular, I think there are 4 issues that I'll try to talk a little bit as we go, right? Are there or can there be such things as inconsistent scientific theories, right? If so, how should they be accommodated, right? If there are, right? What kinds of styles of reasoning that underlie whatever processes that go within scientific practice to make sense of those inconsistencies? Third, what are the sources of these inconsistencies? Are there good empirical reasons for such theories being inconsistent, or it's just a mistake, right? And finally, how should we deal with inconsistent applied mathematical theories? I think those are the best shots you can have at genuine inconsistencies in science. And I'll give some examples along the way. Yes?
Is this still about inconsistencies between theories or not?
And at this point, we're going to end up focusing particularly about inconsistency between theories, right? But if it happens that some scientific theory is self-contradictory, then of course those questions also would have to be addressed. In particular, what the status of those theories is inconsistent theories, and what kinds of commitments would they bring. All right, so let's say a little bit about these things you set out the same, right? First, someone may say, look, there cannot be such thing, such inconsistent scientific theories, period. Or if they existed, they couldn't be accommodated by classical philosophical conceptions of science, right? So think about the sort of syntactic approach that logical positivists were so fond of. So in that sense, a theory is a set of sentence closed on the logical consequence. Now, if the logic is classical, an inconsistent theory will be identical with a set of sentences of the language, and triviality then emerges, right? Now, that's the end of the game. Right? I think part of the scientific enterprise is try to draw a line between what's correct or not, true, false. You need to make some distinctions at a crucial juncture. Of course, Luis may disagree at some level, and we can talk about trivialism, but I actually think that trivialists have always been the target against which everyone has been trying to avoid. Right? So it wasn't when classical logicians abhorred.
This is what we might call vicious trivialism, because you're classical to begin with. So.
Yeah, but and they were, you know, but it would be the same even when you get into a per-consistent setting, right? Yeah. Because there also you don't want your per-consistent logic to be trivial, and it can be trivialized in some contexts. So you need to avoid that as well. So the point is, we've been avoiding trivialists from the get-go. Right? It's just that it became clear with the emergence of per-consistent logic that you can still embrace some contradictions without going all the way into trivialism. And that was an important distinction that emerged at that point. Now, alternatively, on a semantic conception of theories, right? When a theory is presented as, say, a family of models, Again, if the logic is classical, an inconsistent theory would have no models, right? So there wouldn't be models of the theory in terms of which the theory could be presented. Again, I'm assuming we're starting with classical logic, because I think that's the logic that scientific practice, to the extent that there is an underlying logic there, is invoking. The practice, of course, typically is a mess, right? So it's not that it's a clear, here's the logic, here are the inferences that are invoking. We have to extract, right? Scientists are just doing informal things, and we try to make sense of what they're doing, right? It's reasonable to suppose that they're starting with something like classical logic. Now, not always, there are contexts in which the logic is not classical from the get-go. Constructivists are doing their mathematics, of course they're not using classical logic, right? But what they end up doing is producing more mathematics, right? And we have to accommodate that. Okay, so even on these classical conceptions, right, of in the philosophy of science, where the underlying logic is classical, the tools are classical, there's no room for inconsistencies. And they respond and say, look, if inconsistent scientific theories cannot be accommodated by classical philosophical conceptions of science, well, so much the worse for them, right? So we need to find better tools, right? So that we can accommodate the data, mainly the data of there being inconsistent scientific theories. But then you may say, well, hey, wait, which data are we really talking about, right? It's being assumed that there are such inconsistent scientific theories, but the question is, are there any really, right? Now, here's the point, we typically don't have scientific theories that are internally inconsistent, right? At least I'm not familiar of cases in which you say, yes, this is inconsistent and that's why we love it, right? Now we're going to talk, the best case I have for this is not of a scientific theory, an empirical theory, but it's of a mathematical theory, right? And I think the early formulations of the calculus are probably your best bet at getting something that is admittedly inconsistent from the get-go, right? And I'm going to talk a little bit about it in a moment.
Exactly.
He was not, well, first, Frege did never develop a set theory, right? He was trying to develop second-order logic, and he stumbled into an inconsistency rather inadvertently, right? It was never his goal, yes, look, we're going to embrace this inconsistent basic law 5, because now I can reconstruct the whole arithmetic, right? So it was inconsistent, and again, it's an interesting case because what we have there is an attempt at formulating a certain logical framework, right? And it didn't work. Again, the point is he stumbled inadvertently into an inconsistency, right? Yeah.
What about quantum theory, for example?
Well, I'm going to talk about that as well, right? Bohr's atomic model, right? And we're going to see, in each of these cases, I think some care is needed to understand exactly what's going on. Now, I think the best bet where you have inconsistency with other theories, right? I think that happens. That's a fact of science. And it's a fact that we should expect, particularly if you're a pluralist, right? Because, well, obvious case, quantum mechanics and relativity are inconsistent with one another, right? They are both theories about the physics domain, and they cannot both be true. So that is something that needs some care, right? But at this point, if it's a matter of a conflict between two rival theories about the same domain, then the issue becomes an issue about theory choice. Which of these theories, if any, is better? Right? That's typically the response that you get in order to try to accommodate those inconsistencies. So let's see whether that happens or not, right? So I'm going to walk you through three different examples that have been exhaustively discussed in the literature on those issues, and try to see exactly where, if any, inconsistencies emerge, right? I'll start with, so one would be from a physics case, Bohr's atomic model, the other two of sort of a more mathematical sort. So Bohr's atomic model, the sort of little planetary model of the atom, has been pointed out as one example of an inconsistent scientific theory, in that case, an inconsistent scientific model, right? Of course, it was inconsistent with electrodynamics. So it's not that it was internally inconsistent, but it was inconsistent with what electrodynamics states. Because according to electrodynamics, an electron orbiting around the nucleus of the atom will collapse into the nucleus in a matter of seconds, right? So the little planetary model that where you have the nucleus of the atoms and the electrons orbiting around it, that little model that Bohr advanced, according to electrodynamics, would be unstable, right? So the whole thing, just a matter of seconds, just coalesce, right? Of course, then Bohr had a little postulate, right? According to which, this is not going to happen, all right? So just to rule out. Now, here's what Bohr says, right, in his 1913 paper. Energy radiation within the atom is not emitted or absorbed in the continuous way assumed in the ordinary electrodynamics, but only during the passing of the systems between different stationary states. So he's offering you, it's not that he's just saying, look, this is not going to happen, and we'll leave it at that. He tries to give an account, right, the best way he can, right? Joe at least offers a look, why you should not expect electrodynamics to apply in this particular context, right? So electrodynamics does apply, but only partially, right? When the systems pass through different stationary states, right? So you make that distinction so that you can say, look, and that would account why this little molecular model of the atom is actually stable, right? Because of the stationary states, the energy radiation within the atom is not emitted or absorbed in the way described by electrodynamics. In fact, electrodynamics doesn't even apply in this case. So you have a matter here of restricting the scope of application of the theory as an attempt at accommodating a possible contradiction between them. So you may say, in that case, you may ask, okay, which of these theories, Bohr's or electrodynamics, should then be preferred, right? Now, you may say, but is this really a matter of theory choice in this case, right? Because electrodynamics in and of itself, it's of course unable to explain the wavelength of hydrogen's line emission spectrum, right? Which is something that you beautifully do with Bohr's model, one of the things that the model so successfully predicts. Moreover, Bohr does invoke electrodynamics in this when he described the shifts among different stationary states. So you assume he needs the theory to say what happens in other moments in the evolution of the system. So his innovation is just to limit the domain of applicability of electrodynamics, emphasizing that the theory doesn't describe the behavior of stationary states. So that's what the model would account for, what happens in these other cases, right? So it's an interesting maneuver that he's operating, right? It's not just sort of embracing a contradiction. There is a sense in which perhaps given the restriction in the domain of electrodynamics he's offering, then you don't have a contradiction, right? What we have in a way is a division of labor, of explanatory labor. What accounts for what happens between, say, changes between stationary states and when the stationary states are in place. So in that sense, Bohr's model is not internally inconsistent, right? In a way, it's perhaps not even inconsistent with electrodynamics, right? It just restricts the domain of applicability of the theory, right? Of course, it would be if you say, no, electrodynamics is a universal theory that applies to everything, also in particular apply to this model, right? And so, okay, so say, yeah, no, that's true, right? And that's why people were sort of shocked, right, to what he was doing, right? But with that maneuver and his little explanation why, there's no energy transmission in this context, why you say, look, so you're not expect the theory to apply there anyway, right? So in that sense, there wasn't even inconsistent with electrodynamics, right? Of course, if electrodynamics apply to the description of stationary states, then of course we would get an inconsistency, right? Because Bohr's model would be both stable according to his account and unstable according to electrodynamics. Okay. However, if electrodynamics doesn't apply to the domain where the two would diverge, then Bohr's model would not be inconsistent with electrodynamics, right? So, because there's no inconsistency to be derived at this point. So, this is one idea, right? So, by restricting the domain of application of certain theories, you can avoid the inconsistency. Let's consider a different case, but similar. It's different that this is, it's the case of Dirac's delta function. It's another case where inconsistency was allegedly introduced. And this is it's a case that it's halfway through between a mathematical case and a physical one. The whole point of introducing this function is to offer certain expressive formulations for quantum mechanics. And it has some similarities, but also some differences with Bohr, right? So now, what is the delta function? Well, first, it's this little thing. So you have a function that is zero everywhere, except when you get to the zero, the coordinate, where at that point, the integral of the function is so high that it gets to 1, right? And this is how Dirac, in his lovely way, describes it. Right? He says, to get a picture of the delta function, take a function of the real variable x, which vanishes everywhere except inside a small domain of length epsilon, say, surrounding the origin x equals 0, and which is so large inside this domain that its integral over this domain is unity. Right? Clearly has a very clear picture of what he wants this function to be. But of course, he notes we need to be a little careful here, right? And he says, the delta function is not a quantity which can be generally used in mathematical analysis like an ordinary function, but its use must be confined to certain simple types of expression for which it's obvious that no inconsistency can arise. So he was very clear about what he was doing here, right? He was very clear that if you leave this little object, this little mathematical object unconstrained, you're going to get into serious trouble, right? So all the song and dance that he's going to introduce is how you can use it and get rid of it. So you can have your cake and eat it with this little mathematical device. So you have a story about how you can dispense with the delta function. And the crucial property that that function has is the following, right? If you have a continuous function f, right, within the integral, you can actually apply the delta function given this continuous function, and then you can calculate the value of that function. It's going to be 0, and get rid of the delta function as a result. So as Dirac says, we can easily see the validity of this equation from the above picture of the delta function. The left-hand side of the equation can depend only on the values of the function very close to the origin, so that we may replace the function by its value in the origin, 0, without essential error. Right? So in a way, it gives you a strategy in which you can then get rid of the delta function after you've done what calculation devices you need to do with it. In this way, you can dispense with it. So what's important here, Dirac is both aware of the problem that it would emerge if you leave this function unconstrained. Secondly, he knows how to specify a strategy in which you can get rid of the function in those contexts. The third case. This is a sort of a purely mathematical case. Again, it's a case that was motivated for, at least in some cases, for empirical reasons. It's another case of inconsistencies. In that case, in mathematics, that was motivated to make sense of science. And you have here the early calculus. As I said, I think this is your best bet, right, at getting a genuine inconsistency in science, right? So the early formulation of the calculus has this potentially consistent theory. Why? Well, we have the following thing. So it actually makes the formulation of the calculus very straightforward. If you have these quantities, they are always positive, right? But it's smaller than any other quantity, right? Really nice, useful thing to have, right? And they were key for the formulation of the calculus, both for Newton and Leibniz, in slightly different way, and I'm going to mention that briefly. But of course, due to the potentially inconsistent behavior, it's not surprising that their introduction was extremely controversial, right? Berkeley gave everyone a handful in the analysts over this, right? Saying, look, you guys are really messing things up by introducing these kinds of quantities. I'll give you an argument in a minute. And it's not surprising that Leibniz, despite you invoking them in the formulation of the calculus, considering explicitly, this is one of his words, considered the infinitesimals as useful fraction, right? Which made L'Hopital completely insane. He said, what do you mean it's a useful fraction, right? You make these things up and then you're not committed to it. And Leibniz says, yes, that's what it is, right? And now, here's the kind of nice work that infinitesimals can do for you, right? Suppose you are, in the process of differentiating a polynomial of this form, right? And you have your familiar definition of differentiation, right? So you apply the definition to this polynomial, you get this equation, familiar. With a little simplification, algebra, you get this equation here. Now, then you get something quite interesting, right? Because now you have infinitesimals on both sides, and then you say, infinitesimals are always positive, right? So we can divide by them on all counts and get to this guy, right? Infinitesimals are 0, right? It's so smaller than anything, so you can ignore them, and then you get this, right? Which is exactly what you want, right? Anyone who has done a course in calculus would know that, to differentiate this polynomial, you get this, right? And you get a nice little proof of doing that if you have infinitesimals, right? So far, so good. And in fact, you find this very early in the history of calculus. This is the derivation that Berkeley was actually pointing out in the analysis. But here's some care, why you need some care here, right? Because you can say, look, since infinitesimals are 0, we can easily have 1 times an infinitesimal equals 2 times an infinitesimal, right? No problem there, right? But also, if we assume that the infinitesimal is non-zero, we can then divide by it and establish that 1 equals 2. Now, that's bad, right? It doesn't matter, even if your logic is very consistent, you run into trouble if you have 1 equals 2, right? So it's no wonder, right, that you have to be very, very careful when dealing with these kinds of objects, right? Otherwise, you do get, again, triviality. Triviality, end of game, right? So you want to avoid that at any cost, because then you're unable to draw distinctions anymore. Now, here's what I think it's absolutely important. And something that I think is really needed is to understand how is it that Leibniz and Newton, operating with a theory that was clearly inconsistent, managed to get exactly the right theory about differential integral calculus. I think we need to offer an account for that, right? How is it that reasoning in terms that they were familiar with, we can make sense of how they managed to do that. Because here's what, Leibniz is a very interesting case, right? When in 1684 he introduced the differential calculus, he very carefully did not mention the infinitesimal in the explicit formulation of the calculus, right? So in this way, you can think that maybe he's trying to avoid foundational words, right? It was complicated enough just to get the calculus off the ground, right? Why bother bugging it down with with a notion that it's highly controversial, right? And what he did instead was something quite interesting, right? He introduced some rules for you to operate with differentiation and integration, right? Almost a kind of algebraic approach. Of course, this algebraic approach is very familiar to him, given his idea of mathesis universalis, the idea that you have sort of universal picture about logic in the background. So it's not surprising that he would think about that as well, right? But given his pronouncements about the worries that infinitesimals have, it's not surprising that he tried not to bring infinitesimals in the upfront, right? Interestingly, he never really offered a proof of these rules. Which rules? Well, all the rules that we know and love in the calculus, right? It's all there in Leibniz, right? For anyone who has done some calculus, you see those things, and you see, yes, those are the rules you have. This is exactly what Leibniz set up, right? And they're all there, right? Now, you may say, so he didn't use infinitesimals, so what's the fuss is all about, right? Well, it turns out that clearly he presupposed infinitesimals, despite his attempt at not explicitly present them, right? Incidentally, that's a strategy that you're going to find throughout up to the 18th until the 19th century, right? When you have people saying, oh, it's okay to use infinitesimals in the proof, as long as it's not in the statement of the theorem, right? So you have all these kinds of intriguing maneuvers that mathematicians were doing until Cauchy and Weierstrass eventually got rid of infinitesimal with the formulation of analysis, right? To the horror of our current students, first-year mathematics students, right? Because now they have to go through the calculus through epsilons and delta, right? Which is incredibly counterintuitive, right? But you get rid of the infinitesimals, right? So you have a price to pay here. You may get a consistent formulation of analysis that is not as intuitive, or you can get something that is very straightforward, but inconsistent. You choose, right? No, but Leibniz was making a choice, and the choice he was making was, I'm going to invoke infinitesimals on the interpretation of the calculus, right? Not in its formulation, because it was very clear he was offering a kind of geometrical interpretation of those curves, right? When he was talking about dx and dy, he was considering infinitesimal differences, right, between the values of x and y. It was very clear that it was passing the ratio between the x and the y's, right? It was then considered this as a slope in the curve, and you find the diagrams that it was operating with this, right? So it was very clear that, the notion of tangent, right, would invoke infinitely small distances. So it's very clear that he's thinking in terms of infinitesimals throughout, even though when he presents the rules, he never mentions, right? I bet that if he bothered to prove the rules, he's probably going to need to invoke infinitesimals, but he never offered those proofs, right? So I think by thinking about these potentially inconsistent infinitesimals, Leibniz did manage to devise correct rules for the differential calculus. And that's what puzzles me. That's what I would like to understand. How can we make sense of why is it that he managed to get the right rules operating in an inconsistent setting? How can he do that, right? Okay, you can say, look, you can reconstruct this with a personal system logic, right? And you can, and it has been done. But of course, this is not the way that Leibniz was operating, right? There was no concept of very consistent logic in the 17th century. It's highly anachronistic to say, yeah, that's how we can reconstruct what he was doing. Yeah, we can, but that's irrelevant. That's not what he was doing. I understand what he was really doing, how he managed to do what he did, despite operating in an inconsistent setting. I think that's the question we should try to understand. Now, Newton is another interesting case, right? And here, even more than Leibniz, right? You read the Principia, and he was very careful to offer all the proofs geometrically, right? In order exactly to try to avoid the infinitesimals. And here's what he says. Quantities and the ratios of quantities which in any finite time converge continually to equality, and before the end of that time approach near to each other, then by any given difference, become ultimately equal. Now this is beautiful, right? In a way, what this reminds me is the first principle of L'Hopital's calculus textbook, right? Published in the 17th century. And that principle says the following: if two quantities differ by infinitesimal, then they are the same. Now, of course, this is obviously inconsistent, right? If two things are different, they are the same, right? Of course, they want to, again, you understand, well, they differ by something that's so small that you can ignore it, but it's still, you're basically saying the two things that are different are the same. In a way, this is what Newton is acknowledging here, right? You have these quantities, as long as they are vanishing very closely. Now, that's the notion of infinitesimal right there, and they are the same quantities, right? And then he clarifies that a little bit later. For demonstrations are shorter by the method of indivisibles, right? So you can get better results and shorter derivation with them. But because the hypothesis of indivisibles seems somewhat harsh, so he's already, of course, he's aware that the harshness are really in the statement, right, about what's going on. But because the hypothesis is harsh and therefore that method is reckoned less geometrical, I chose rather to reduce the demonstration of the following propositions to the first and last sums and ratios of nascent and evanescent quantities. That is to the limits of those sums and ratios, and so to premise as short as I could the demonstration of those limits. So he's there doing this little song and dance, right? Trying to say, okay, look, acknowledging that infinitesimals are problematic, telling a little story about how you can try to run your proofs, without them the best you can, right? And of course, those things then got Berkeley really annoyed, right? And Berkeley then said, look, you need to get your act together. This is just unacceptable. Right? Okay. Of course, probably we would not be having this conversation today if the Principia had been a massive failure, right? But because of the incredible success that Newtonian physics has had, now the issue became, okay, now what do? We have this theory, physical theory, riding on the back of an inconsistent piece of mathematics, right? And it took 200 years until people got rid of the infinitesimals in the end. This, I think, is the best case we get to deal with inconsistencies in science, right? Note that the kind of inconsistency we're dealing with it's actually an inconsistency it's an internally inconsistent mathematical theory that is being used in order to conceptualize some physical notions. So it's a little more complicated than any of the models, right? But that's, I think, is what at issue in this case. Now, as we all know, there are those people who said that no cases whatsoever of inconsistencies in science, right? And Peter Vickers is, in his 2013 book, try to offer a defense of this case. We talked a little bit about it yesterday in Maria's and Luis's paper. And he says, we have seen that the number of significant inconsistencies which exist in real science is far less than has often been suggested. The main examples of significant inconsistency in this thesis are the later Bohr theory of the atom, Newtonian cosmology, and to a lesser extent, the early calculus and Kirchhoff's theory of diffraction. Yeah. Here he should have said this book, right? The book is based on the dissertation that he defended and elaborated further. And then he continues, right? But in each of these cases, it's clear that scientists don't avoid the conflict by changing the logic. As the case studies have shown, classical deductive logic is used. Rather, it's implausible that scientists should handle these cases by changing their logic. All that might be said is that these cases can be reconstructed by changing the logic, but it's hard to see what understanding might be gained by such a reconstruction. Okay? Now, I think it's a little too harsh here. I think there is some understanding you can get, right, by reconstructing the arguments in a paraconsistent settings. I think they would at least explain how you can entertain the inconsistencies without triviality, right? Which is no mean feat, right? So that's important. What they do not do, however, and I think that we should be acknowledged, is explain in terms of the practitioners themselves, how they managed to do what they did, which I think is a fair question. It's one that I would like to see answered, right?
Because they never used classical deductive logic.
Well, but at least it was a logic that was available to
We
them,
can
right?
reconstruct,
Yeah,
we can show that they did something that.
that's right. But they're, at least it's a logic that,
Deductive logic.
right. Well, yeah, they don't have.
By Frege, my
They,
Frege.
yeah, they don't have logic, in the way that that from Frege did. That's correct, right? But they do have inferential patterns, right? That are clearly deductive valid, and so in, at least I think it's a less of an anachronism, right? To say, look, they're operating with something that is like classical logic, and to say they're operating something that is very consistent, right?
But he's not that nuanced.
Sorry?
He's not that nuanced.
No, but fair enough. Yeah, no, I'm not defending the view, right? Right. And my point is to say, I think there is something. So look, the three cases I mentioned are illustrations of. We need to be careful here, right? I think sometimes folks in the paraconsistent tradition have overstated their case about inconsistencies, right? Some cases, folks in the classical tradition have understated the case for inconsistency. So I think that it's somewhere in between, right? And I try to suggest that something a little more nuanced is actually going on once you look at the actual details of the inferential practices involved, okay? Now, having set this up, we can now consider the issue of how to accommodate inconsistencies, right? I'm going to briefly sketch 4 different strategies, and we're going to assess to what extent they are appropriate or inappropriate. Right? So first strategy, it's sort of, they're a class of consistency preserving strategies, right? Those are strategies that insist that scientific theories are not inconsistent. They cannot be because classical logic is assumed, right? And there are 2 different ways you can think of how to proceed here, right? One is by compartmentalization, right? You preserve classical logic, and you divide up scientific inquiry into different domains, right? And divide up in such a way that these domains do not overlap. And in that way you block the inconsistency, right? So you define clearly and compartmentalize without overlap. This would generate a kind of consistent disunit pluralism. Right, so you have a pluralism in the sense I talked in the beginning of this talk, because you have different domains, right? The underlying logic is classical, but each domain, because it's non-overlapping, would avoid the inconsistency. And it has to be disunified because the domains will have to clearly cut between them. A second consistency preserving maneuver will be a sort of information restriction. Again, you keep classical logic, right? But you say, look, but there is a single domain. One huge domain that what the scientific enterprise is trying to come to grips with, and you avoid the inconsistency by somehow eliminating and extracting the conflicted information, right? So that's another strategy. It would yield a form of consistent monism, right? Monism, there is one single domain, right? No inconsistencies are there because you're getting rid of them however you can, and it's a monist picture since there is one and only one domain. Okay. Okay. In both cases, you're dealing also the compartmentalization strategy, as I'm presenting here, is also monist in the logical sense, right? Because there is a single logic. Now, the other strategy, the other 2 strategies are inconsistency tolerant strategies. They acknowledge that, yes, there are, and it's possible that there are inconsistent scientific theories. And there's, again, 2 possible maneuvers there. One is a sort of a paraconsistent compartmentalization, right? there are inconsistent but non-trivial scientific theories, right? So you assume a pair-consistent underlying logic, so you can let the inconsistencies unfold without triviality, right? But there is a plurality of domains. The difference is you allow some of those domains overlap, and that's where inconsistency will often emerge. So you have a sort of a form of pluralism because there's a plurality of domains. Inconsistency because it allows inconsistency and is disunified, right? Because there are different domains, right? There's no one overarching picture. And the final view, a form of dialetheism, right? Again, you need to adopt a pair-consistent logic because you're taking the scientific theories as being inconsistent without triviality. And then you take there to be a single domain the scientific enterprise is trying to come to grips with, and then you try to identify which inconsistencies, for which inconsistencies there are good reasons to believe. And those you embrace. Other inconsistencies, you may not have good reason to believe, you just rule them out. Right? This generates a form of inconsistent monism, right? It's a single domain, but allows for inconsistency. In this case, of course, the dialetheism is not only a monist in the sense of theoretical monist, but also will be a monist in the logical sense. There's a single underlying logic here. The pair-consistent compartmentalization will be a pluralism, both theoretical side, but also in the logic, because you would allow multiplicity of pair-consistent logics getting into here, right? I would put Diedrich here, right, as part of that strategy. Okay, you didn't like it. All right, so we need to find a new category.
I have a question.
Yeah.
So the underlying logic for accepting several domains is very consistent, but each domain have to have a very consistent logic behind?
No, not necessarily.
So it could be any other logic.
That's right. And that's where you get a logical pluralist picture, right? Because you have multiple logics floating around, right? So, and in fact, well, I have a paper I published a long time ago. I think every logical pluralist has to be a pair-consistentist, right? Oh, sorry, and the other way around too. The paper actually argued for why every pair-consistent theorist has to be a logical pluralist, right? And of course, Graham disagrees, but that's the target of that paper. Right? Okay, I think there are problems for all four strategies. So none of them is actually problem-free. Right? There are some advantages as well. So let me just briefly point them out. So here's some costs, right? First, sort of generic costs for the consistent preserving strategies, right? I'll get into the details of each maneuvers in a second, right? Of course, as I try to suggest, some of the data seem to support the existence of inconsistent theories. To the extent that those strategies try to rule them out, they're going to be empirically inadequate, right? They have no room to make sense of those inconsistencies in their own terms, right? I think that's bad. As I mentioned, infinitesimals just seem to have inconsistent properties, right? Even if you said, oh, but wait a minute, Abraham Robinson, when he introduced non-standard analysis, cleaned them up and show how you can have a consistent theory of infinitesimals, right? Fair enough, you have non-standard models, and in those non-standard models, you have objects that have properties that you can interpret as being properties of infinitesimals, right? But in order to create these non-standard models, you have to have an underlying model theory and a theory of enlargements over which you can run these models. Yeah, in fact, you require at least third-order logic in order to get these models. That obviously has nothing to do with what Leibniz was doing, right? And it'd be highly anachronistic in the way that Robinson did to say, oh yeah, we can realize Leibniz dream now, and then he reread non-standard analysis as something that worked out Leibniz's position, right? I think that's, even though I really like Robinson's work, I think that as a piece of historical analysis, just a non-starter. Right? And of course, also, you lose, what makes infinitesimals so easy to operate with is exactly their inconsistent properties, right? It's hard work doing non-standard analysis in the model theoretic framework that you have to operate within it. Again, you lose that when you have a consistent version. Same choice, right? Consistent awkward theory to operate with, or straightforward theory to operate with, but inconsistent. Okay. Now, the other case of inconsistent theory is, of course, quantum mechanics and relativity theory, right? Well-known case, which those consistent preserving strategies would have to fly in the face. All right, so specifically to the compartmentalization strategy, some crucial information, I think, may be lost when you implement the compartmentalization, right? So, because some contexts may require information in overlapping domains, right? So, for example, what happens to a quantum particle when they're subject to huge gravitational fields? Right? You may need both quantum mechanics and relativity theory to tell a story about these things. So, if you compartmentalize them, separate in different domains so that there is no conflict, you actually may lose relevant information. Of course, you can come up with a different theory, right? But that's a different strategy altogether, right? That's to change the context. And of course, good luck going there. Now, also, compartmentalization will be entirely ad hoc, right? If you devise it just to avoid inconsistency without independent motivation. So you have to be very careful there, right? If you want to restrict the scope, you want to tell some kind of story about why is it you have some independent reason to do it. In a way, Bohr was very careful when he was trying to compartmentalize a little bit the domain of application of electrodynamics. He was trying to tell us some story about, oh, look, that's no transmission of energy here. Don't expect electrodynamics to apply there, right? So that's an attempt, right? But at least it's stipulation. Yeah, that's right. Yeah. But that's the concern, right? Whenever you're invoking this sort of compartmentalization. Now, I should grant the compartmentalization strategy does have one important benefit, right? As I noted, it does lead to a form of pluralism, theoretical pluralism, given the various domains that it allows for. And I think this is a significant feature of contemporary science. So I think this is a good trait, right? Even though the rest is, I think, seriously flawed. Okay, how about the information restriction strategy, right? You have a single domain and you restrict somehow the information to avoid inconsistency. The logic is too classical. Again, crucial information may be lost when you extract it in order just to preserve consistency, right? In fact, that's the usual story, right? You can get your consistency, but you lose informativeness. Right? Are you willing to pay that price? Right? Also, this extraction of information can be ad hoc. Right? If it's implemented just to avoid inconsistency with no independent motivation, well, the epistemic value will be similarly limited. Now, importantly, sometimes the only way of obtaining information is by exploring theories inconsistent with accepted ones. Right? A bunch of possible examples here. One obvious case is what Galileo did, right? Of course, the accepted theory at the time was Aristotelian physics that tells you, look, there is this fundamental difference between behavior of celestial bodies and objects near the surface of the Earth. The fact that your telescope works well in the Earth has nothing to tell us about it gives any reason to believe what you're seeing beyond that domain. Of course, Galileo just ignored that. Good for him, right? But what he was doing was actually going against the accepted theory and operating. He basically, on no much evidence at the time, he basically assumed that Aristotelian physics is wrong, right? And we're going to operate from there. But developing an alternative that actually was inconsistent with the accepted theory. Of course, Feyerabend does a great job at exploring that in his funny way. All right. He's the only author, by the way, in which you can get on the same page discussions about quantum mechanics and Homeric gods. But it kind of all makes sense. All right. So I think strategies that involve information restriction can be highly ineffective right? In the sense of as strategies that to be incorporated in scientific practice. Of course, as I formulate the information restriction strategy defends a form of monism, right? Which, as I noted, with a single consistent domain, ends up conflicting with contemporary science, and I think that's a big cost. Now let's look at the inconsistency tolerant maneuvers, right? First, we have the per-consistent compartmentalization, right? One cost it has, I already alerted to, you have anachronism, right? If you're using per-consistent logic, say to reconstruct inferences in the 17th century for the development of the calculus, you're actually assigning inferential devices that were not available to the folks who are actually doing the reasoning there. So there's a sense in which you're sort of creating a parallel discourse, right? You're creating something that's perfectly fine, right? Look, I love per-consistent logic. I'll be the last one to not like it. But we need to understand the limitations depending on what you're trying to do with it, right? If your goal is to understand how Leibniz, in his own terms, could have developed the form of calculus, if you say, yeah, reconstruct his reasoning in per-consistent logic, it's not going to answer that question. Right? You answer the modal question, namely how a counterpart of Leibniz could have developed the calculus had he access to per-consistent logic. But that's a different question. Now, so at best, I think we have a framework to represent artificial reconstructions of reasoning involving the introduction of the infinitesimals. The actual reasoning is still left behind, right? Moreover, the underlying logic is hardly ever made explicit, right, in scientific practice, which results in a highly idealized strategy, right? That's going to be true of any formal approach, right? And that's a cost that needs to be acknowledged, right? Now, we do have an important benefit, and I don't take that lightly, right? As I noted, the strategy will allow for a plurality of overlapping domains. And I think this kind of pluralism jives very well with contemporary science, and that's an important beneficial trait of the field. Finally, we have the dialecticist approach, right? Now, I think it's unclear that scientific theories have ever been embraced on the grounds that they yield true contradictions, right? That's what you would expect, right? You say, yes, this is a dialectic account of scientific practice. Nowhere, I think, in scientific practice is a strategy, in fact, implemented, right? We don't find, as we find, for example, with Graham, right, when he argues for, look, we need to embrace the conclusion of the liar paradox, because that's, on his view, the best and only way of making sense of what's happening, right? So you have to embrace there are true contradictions, otherwise you cannot preserve the phenomenon. I don't find anything remotely similar to that anywhere in the history of science, right? Which is what you would find, or expect to find, if you were offering a dialecticist approach to scientific practice. Now, I think this also would lead to, as I noted, a monist field, right? Which, since you have a single domain, right? In his case, even a single underlying logic, which I don't think allows us to make sense of contemporary science properly. And moreover, I don't even think the dialecticism is even needed, right? If you're inclined toward an inconsistency tolerant view, which you should, then I think your best bet is to go with the per-consistent strategy, right? Because that would allow you to operate under, account for reasoning in inconsistent settings without triviality, without arbitrarily eliminating bits of information, which is what you're stuck with if you try to run one of the consistent preserving strategy, but also without the commitment to true contradictions, which is what you're stuck with dialectics, right? So there's a sense in which you don't really need to go that far, dialecticism, if you're inclined to make sense or take seriously inconsistency in science. Having said that, of course, the per-consistent strategy still face the difficulties I mentioned in terms of the anachronistic and the reconstructive strategy of reasoning. So that has to be addressed as well. So, 2 minutes and I'll shut up. Here's what we can gain from these, cursory survey over a little bit of the history of inconsistency in science, right? I think looking at the practice out of the three cases I considered, we find sort of two complementary strategies, right? There is one of dispensability and one of domain restriction, right? We found, in the case of infinitesimals, ways in which they can be dispensed with, right? So we saw Leibniz saying this is a useful fiction. We saw Newton trying to come up with a story about, okay, he's all going to try to avoid their use. Of course, it's not enough to go ahead and say that. You need to offer an account. Why is it okay to use these devices and then get rid of them, right? On that score, I think as will become clear in a minute, Dirac had a nice little story, okay? Like, of course, it's a mathematical story about how, under what conditions you can really dispense with. You want something like that, right? Something that will allow you to have a principled reason to say, yes, I'm invoking these things, I realize they're problematic. Here are the conditions under it's okay to use them, and here's why I'm only operating under those conditions, and how I get rid of them. Once you have that, at least you have a story why it's safe to use as sort of useful devices, right? As Leibniz says, useful fictions. These potentially problematic and inconsistent objects, right? So that's one strategy, but it needs to be fleshed out because you need to tell a story about under what conditions this dispensability will take place. The other one is that sort of domain restriction that we found in the case of Bohr's atomic model, right? There he clearly was sort of restricting the scope of electrodynamic theory. Again, you need to offer some kind of account. We saw that the account he offers sort of, it's kind of ad hoc, so just imposing that this, it's not ideal, but at least he felt the need for saying something, right? So in the highlights that he understood what the complexities were in place there. And of course, I think you find both things in the delta function. In many ways, it's, of the three cases I discussed, is the most successful, right? Because you do find a domain restriction, right? Dirac telling you, well, look, only operate with this function within the context of the integrals, and you can dispense with them in this context, and it tells you a story about them as well, right? So that's the sort of thing that is needed. You understand the condition. In a way, sort of, those are conditions of introduction and elimination of these objects, right? So you can know when it's safe to operate with them, right? Now, in thinking about the application of mathematics, I did some work with Mark Oliver. We developed what we call an inferential conception of the application of mathematics, which I think offers a little framework that we can sort of embed some of those moves, right? So the idea basically is you have a sort of an empirical setup, and you select certain features of that setup and map them, immerse them into a mathematical model, right? It's a mathematical structure. Now that mathematical structure will have its own internal inferential dynamics, right? There's a mathematics, there's an underlying logic, and you can actually derive certain things with it. Once you derive, of course, the mathematics doesn't say anything about the physical world. You have to interpret the result back. In reality, you see what it says. Now, the function that it led to immerse some parts of the empirical setup into a mathematical structure need not be the same one that you need to use when interpreting the results you got back. What's important here is to be very careful when you think about setting up this mathematical structure. And that's where the sort of constraint, the limitation in scope, and the dispensability will come, right? It's in these steps, right? So, and I think that's a framework when you can think about applying inconsistent mathematics. Should look for exactly where are the maneuvers that allow these objects to be introduced, used, inferred, and then eliminated. And if you can do that carefully, you can at least understand how you can get the result. Of course, you're not going to get a one-fits-all story here, right? As with any good pluralist, right? You have local stories, right? So this is a sort of a schematic framework you need then to flesh out in each case with the appropriate details and the appropriate justification for the dispensability of the objects in question. So to conclude, I think more work needs to be done in the attempt of making sense of those cases in which inconsistencies emerge in science. On the one hand, formal approaches are clear and tractable, but they add an extra layer of structure that is no part of scientific practice. I think that's a cost. On the other hand, informal approach, despite being closer to the practice, can just be as confusing and unclear as certain traits of the practice themselves. So they may not be illuminated. That's not good either, right? So the challenge that we find is to find a middle ground here, right? A proper balance and an illuminating account in which features of the practice allow one to deal with inconsistencies in a proper way, illuminating the maneuvers invoked in the practice, in a way to help us understand how you can really reason about inconsistency without triviality. Thank you very much.
Michelle? Yes.
Wait, I don't know which, I have two questions, so I'll let you just choose one and I'll think about the other one. So one of them has to do with this. Well, no, I'll just ask the one that I have foremost in my mind. So in the last slide where you have this notion of immersion and interpretation, there's going to be several versions of this, right? Because as you said, you have to be careful about which mathematical structure you choose. So there are going to be different ways of immersing and then different ways of interpreting, etc., etc.
Yeah.
So how do you choose between those?
Good. I think that's an issue about the modeling, right? So typically what will happen is sometimes you are forced to choose because some possibilities are mathematically intractable, right? So then
Where you can eliminate some, but there's still going to be a
that's right.
infinite number of these.
That's right. And then sometimes what you do is you explore all of them. And you see which of them yields results that are illuminating or helpful. Often you don't know in advance.
Right. Or you might use this notion of satisficing, but it's good enough for now and it's doing the work that I need it to do, so it's okay.
That's true, right? So I think, because at that point, we are in the domain of heuristics, right? In the domain of trying to figure out how best to represent this phenomenon.
Best
right?
is a term of
No,
art.
yeah, best, yeah, not, yeah, that's right. So, and it's not that I don't think there is nothing to be said about it. I think there are lots of things. Sometimes, for example, you can use structural similarities. And they say, look, this phenomenon is similar in this respect to this other one. So it suggests that we can invoke this piece of mathematics that was successfully applied there and bring to this context. And that's how people use results from biology and economics and right, that kind of stuff. Right.
Sergio?
Yo?
Sí.
Yeah, I have one question about your use of inconsistency.
Okay.
Because you seem to be using inconsistency in different ways
Mhm.
and applying to different things, and I don't see how they relate to each other. For example, you talk of inconsistent properties, inconsistent concepts, inconsistent theories, and I don't see obviously how they connect these different notions.
Well, I think they are, yeah, I agree that on the surface those are different things, but I think you can, in all of those cases, bring together, right? An inconsistent theory is a theory from which you derive A or not A, right? An inconsistent concept is a concept in which the extension and the anti-extension of the concept may overlap, right?
But in the case of infinitesimals, that is not the sense of inconsistency that is at stake.
Well, in the case of infinitesimal, the worry there was you derive contradictions by adding these objects to your formulation of the calculus.
I can say that's one way of showing that there is a problem with the concept that doesn't fit into a notion of analysis or mathematical analysis that ideally we should have. And there are different ways of dealing with the problem. But it could be just, say, help for diagnosis, what you characterize inconsistency.
Yeah, well, fair enough. Look, of course, I'm using, I agree, there are different ways you can, in fact, even the notion of contradiction also depends on the logic. There are all kinds of different things you can say that, right? I don't think that anything that I have to say here cannot be said, however you want to flesh that out, right? I think there are some ways that might be more natural than others, right? In the case of the infinitesimal, that's the way I was operating, right? Which I think is the way that in the 17th century they were thinking, right? Because you add these extra objects in your formulation of analysis, and suddenly you could get inconsistencies that you could not without, right? So that's one sense in which the objects now become inconsistent, right? Or the concept, if you want to talk in that way. So I didn't spell out the sense because I think however you want to do it, you can get the results. Just some ways might be more natural to do it than others.
Michelle has a follow-up.
Yeah, so exactly on this sort of point. If Leibniz's views on the infinitesimals is very obviously inconsistent if you have a sort of medium-sized dry goods notion of the physical world. But if you think more in terms of chemistry or something, it's not so obvious. So you think about purity of a substance, right? That's going to be sort of diminishing returns on the purity of a substance. So, and it can be neglected at some moments, right? The substance is actually impure. So if Leibniz was thinking in terms of chemistry more than in terms of medium-sized dry goods that inform, so this is almost a metaphysical difference, right? And so if your metaphysics is informed by the idea of objects being clearly and distinguished, the identity properties are very obvious all the time, then you run into these contradictions that Berkeley was aware of. If you have a more chemistry informed metaphysics, then those problems go away. And I don't think Leibniz was ignorant of chemistry. So even at the time,
yeah, I think the way he was operating was clearly that he was thinking, of course, there was this business when he was interpreting the curves, right? In the slope of the curves, the tangents. But also you have the actual use in derivations of the infinitesimal. For that, what matters is those are positive magnitudes that are smaller than any other number. And that it's operationally, that's what's crucial, right? Because then you do the kinds of use I just mentioned, right? And then it's sort of kind of independently of what kind of metaphysics you have, what infinitesimals are. Because what matters for those inferential purposes is whether an infinitesimal is positive and whether it's it's more than any other one that it's negligible. And I think I think he realized that's what he needed for an inferential purpose. That's why he tried to avoid explicitly adding those things there. But no matter what metaphysics of infinitesimals, they would stand that these are the relevant mathematical properties that they have. And that's what bugged, I think, rightly so.
But calling them mathematical properties, right, you're already imputing a certain metaphysical view on mathematics.
No, not necessarily, because I'm thinking of them in terms of inferential power, right? Because to do that little inference
right,
and show.
It's not inconsistent if you allow that.
No, I think that, I actually think that the mathematics is neutral on the way you're going to interpret it.
Yeah, we often think that.
Yeah, well, I think it is. So you can offer different interpretations. The derivations are going to go through however you want, right? If they're valid, they're going to go through. And even though the mathematics is often interpreted, right, And so I'm not saying that mathematics is this domain of uninterpreted calculus, that would be silly, right? But the kinds of interpretations the mathematicians offer are not the kinds of metaphysical pictures that you're referring here. I think it's something much sort of minimal in that sense. And ultimately, what they really are concerned with is what the inferential devices that are at stake.
Sorry, we have 3 more questions.
Oh, okay, I'll try to be brief. We'll talk.
Yeah, sorry.
Armando? Well, I have a worry. It seems that the various paraconsistent strategies may promote a sort of epistemic self-indulgence or permissiveness. Instead of working to eliminate inconsistencies, one tries to live with them. For example, in the case of infinitesimals, well, mathematicians eventually eliminated them, say by Dedekind's work and so on, because they tried to eliminate them. And another example, Copernican heliocentrism was originally inconsistent with Aristotelian physics. Well, the search to avoid or eliminate inconsistencies led to Newtonian physics. Finally, I finish. Pluralism may be a fact of contemporary science, or let's say is a fact of contemporary science. But the question is, should it be the goal of science?
Good. No, those are great questions. So first, about the paraconsistency. I don't think the idea of paraconsistency is you say, look, embrace the contradictions and you're home free. No, I think the way I think of it, and I think several paraconsistent logicians would agree, is you use paraconsistent logic as a device that would allow you to reason with an inconsistent domain without triviality in order to figure out what went wrong and eventually clean up, right? So I think it's an inferential tool in that sense, right? You need not be
only for the time being.
Well, otherwise you don't have other resources, right, to reason. If you have a contradiction and you're stuck with classical logic, you have triviality, right? So then you have to do one of the things I mentioned. You have to avoid the information, eliminate information somehow, right? Or pretend that there is a. So while you figure it out, a consistent setting, it will be helpful, right? At least that's the way I think of it. Now, should science be pluralistic, right? And I think it should. In fact, I don't see how you can bring together things as diverse as quantum field theory and pediatrics, right? And and I think that if the cost would be, okay, yes, you have to bring it all together in a way that either it's going to be at such a high level of idealization that we're not really talking about science, or you have to chop off whole chunks of science, and either one doesn't seem.
Well, but physicists are searching for a unified theory of.
And even if they manage to find that would tell nothing about pediatrics, right? It tells nothing about sociology, history, right? Very little about chemistry. So, in a way, sort of, it is a misnomer, right? Yeah, a theory of everything. Well, it's a unified theory about physics, right? But there are lots of other things that are not physics. In fact, most of science is not physics, doesn't operate like physics. So, that's not monism.
Well, it could be an ideal. Monism is an epistemic ideal.
But okay, what do we gain by it, right? Because I think we lose information, and it's precious, right? If you have to bring together things that are fundamentally diverse, right, such as whether you should breastfeed your babies or not, and behavior quantum particles. I have no idea how you're going to put this together in a coherent way.
So far.
Okay, all right.
Joe.
Fair enough.
I have two questions, but I will stick to one of them and address the other one during my talk. But the question I have is concerns your notion of science. When you say that our best bet for inconsistencies in science is early calculus, it seems to me that you're restricting science here to more or less finished models and theories. And if you look at proto-theories and early models, I think you may find much more inconsistencies than if you only look at finished theories.
Right.
For instance, also in the case of Bohr, 1913 is already quite late. If you look at the discussions they had during the Solvay conferences,
Right.
they were really addressing the problem of inconsistency.
Right.
Even Poincaré then pointed out, what are you doing? You're mixing classical mechanics with electrodynamics. Don't you know that if you combine those, you risk
both.
also.
Yeah, great. No, I agree. Look, of course, look, I spoke for an hour. Sorry, let's talk about everything, right? Of course, science involves lots of other things, including theories that are being formed, theories that didn't fly, that were abandoned. There are all kinds of things that need attention, right? Why did I focus on those? Because to avoid the following easy way out that the consistent test could have is to say, oh, look, those theories were eventually abandoned, right? They were not, those are the proto-theories. I assume in the process of being developed and eventually they're going to be given up. So, they play no epistemic role when all is said and done about science. And I don't want to get that response, right? Now, you may say, look, Bohr's model was eventually abandoned, right? But it's interesting, despite that fact, it's still a model that a lot of people think of the structure of atoms in those terms, right? So, despite all the problems. And so I fully agree with you that science is a complex phenomenon, and very different levels of analysis are needed and involved, right? But I want to resist that, at least that kind of dismissive response, right? But say, okay, let's consider something that everyone would grant is a significant accomplishment in and of itself, right? Given the derivation of the Popper sequence and all the kinds of predictive power that we could do with the Bohr's model. Right?
Last one, Bryson, please.
At a couple of points, I wasn't sure. It seemed pretty clear with Vickers that you sort of, he's defaulting to classical logic. That's the background logic.
Right.
And you have to push him very, very hard to get him to even think about the possibility that you might want to pair consistent logic. And so he's starting with a fairly fortified position.
Right.
But a few times I thought in your own discourse, it seemed like classical logic would be the standard background assumption if we were going to perform a kind of logical interpretation of scientific reasoning.
Right.
And I feel personally, I want to be much more conservative about that. I want to say, look, we don't know what logic scientists are using. They're not using explicit logic. Some of them might have been trained in classical logic, but that doesn't mean that immediately leaks through. And if it does leak through, it might not actually reflect the patterns of reasoning they're actually using, because they're following one path or another in the course of the reasoning, not closing under a consequence relation.
No, fair enough. I think I grant your point, right? I think when I said that the practice it's informal, right? The practice there's no explicit underlying logic, right? And my understanding is to the extent that there is one, the default logic tends to be classical, right? At least let's consider since classical logic as such was formulated around the end of the 19th century.
On the basis of the fact of education in classical logic?
In a way, yeah, well, but there's also some reason in terms of the just inferential power, right? And which is something that the scientists will care deeply about, right? And if they can get the results, the machinery that quickly get them there, we'll go for that, typically. Of course, there are always exceptions. That's what I meant when I said, look, we start with classical. It's not a defense of classical logic. I'm actually a logical pluralist. I think there's no way you can say this is the underlying logic. In part because given any finite amount of reasoning, there's a plurality of logics that will validate this reasoning. You cannot tell.
Exactly.
So you cannot tell which is the underlying logic. right? So, and that's one reason why there is a plurality, right? Inevitably, right? But I think by and large the practice tend, at least in the contemporary scene, tends, it may be a factor of education, fine, but it tends to be classical, typically. But for the most part, you have no logic, explicit logic anywhere.
As the organizer has given her permission, Diederik, please.
Oh, it's a bit a silly question, but as you saw from my reaction when you were talking, I didn't feel a role in B1. But you say the guys from B1, so I think you included me there, had given an anachronistic explanation of what happened in the 17th century, because there were no purposes to and also the reconstruction is artificial. Now, I did not talk yesterday about inconsistency adaptive logics. I just mentioned them, but I have talked about it. But what they basically do is they reason sequentially, like writing a proof, and as long as you do not find an inconsistency, you just get the same results as classical logic.
Right.
And if at some point you hit an inconsistency, what you do is there are some conclusions that you don't draw anymore,
Right.
and there are some conclusions that you derive before that you say, oh, I don't want those, I withdraw them, because there's a problem here. Now, what's anachronistic about that, or what is more anachronistic about that than any other?
No, described in that way, I think is perfectly fine, right? The anachronism will come in terms of, now we have a formal setting. We have this hierarchy of logics. And when they kick in, which logic kicks in, to what device, but there is a dynamic.
But any explication of the historical facts in terms of what we today call logic, okay, these are not Tarski logic, but whether it's Tarski logic or a diffeasible logic, is all anachronistic, of course. This is quite obvious.
Yeah, that's what I'm saying.
But
that's the problem. That's exactly
why is that the problem?
Because we conceptualize the inferential practice of these 17th century people in ways that are fundamentally different from the way they conceptualize it themselves.
But you never showed that.
Well,
Can you give an example of it?
yeah, well, one example I mentioned was when Robinson looked at the infinitesimal, right, and say, oh, look, these infinitesimals are actually non-standard numbers.
Yeah, that's Robinson.
Right?
I mean,
that's one example where it's blatantly clear.
No,
right?
Ótavio, what you do now is saying, here's a guy that conceptualized it wrongly. He is an anachronistic.
Right.
Yeah, but does that mean that all
No.
reconstructions are anachronistic?
Okay, in which other ways, right? So you go on and you think, look, here's an inference, right, that this particular guy was using, right? And then you reconstruct, and you give a model theory for on what conditions that the inference goes through, and you develop a whole system that justify why this thing is valid. And now this is all part of the machinery that we are invoking when you say, oh, look, these are the inferences given the contemporary scene. And the way we are conceptualizing those inferences, we are actually assigning a whole bunch of extra structure, which we take for granted because we've all lived in this world, but that has nothing to do with what they were doing. This is anachronistic. Now, you may say, well, don't get the wrong results in doing that, right? Because I can still validate the inferences that they perform. You can, and I'm not contesting that. But you are reconstructing the background of those inferences in a way that it's foreign for the way that it's doing. Well, that's what I'm questioning, right? That's exactly what I'm saying. Look, we have, at that point, we're crossing a line that we have to be careful.
And what
Sorry.
about historians of science?
Sorry.
Also reconstruct.
That's really in there? Yeah, I agree. Okay.
I think we should stop here and talk later during lunch, coffee breaks, and the hotel or something. No, let's thank Ótavio.
Thank you. Thank you.